Welcome everybody to this webinar on quantum safe cryptography. Today I'll discuss how to secure today's data against the computers of tomorrow. My name is Christian Paquin. I am a principal program manager with the Microsoft Research, Security and Cryptography team. So before we begin, I'll talk a little bit more about me, my favorite subject. So we've heard a lot lately about the quantum computer. It's everywhere in the news. It's a big research subject. And I've been hearing about quantum computers for a long time. About 25 years ago, I was a young student at the University of Montreal, where under the supervision of Gilles Brassard, who was a quantum computing pioneer, co-inventor of the quantum key distribution and quantum teleportation. And we were trying to develop quantum cryptography and all sorts of novel ideas. After my studies, I had to take a more practical turn to earn a paycheck. So I went into applied cryptography and into the industry, where I worked for many years as a crypto engineer. And a bit more than 10 years ago, I ended up at Microsoft, and I'm currently in the Microsoft Research, Security and Crypto team. And we're working on cutting-edge cryptography, all sorts of new research ideas that will end up in products and services in 5 to 10 years. Our current focus is post-quantum cryptography, or quantum safe cryptography, which is the subject of this webinar. And excuse me. And so now that you know about me, let's talk about this subject. Quantum revolution is, as I said, a really big subject. Conventional computers are built with the normal laws of Newton laws of physics. A bit is 0 or 1, and you can manipulate it, and we can do all sorts of things with that. But if you build a computer using particles that follows the laws of quantum mechanics, you get all new sets of properties that allow us to build incredible algorithms and solve problems we didn't know we could solve before. So a quantum bit, a qubit, instead of being only 0 or 1, can be 0 and 1 at the same time in a kind of superposition. And also quantum particles, if you make them interact and separate them, they can become entangled. And by manipulating one, you can change the state of the other one. So using these properties, quantum computer experts have developed new algorithms and new ideas and bring forward the quantum revolution. And now that, since we've known a couple last decades what we could do with quantum algorithmics, there's been this race, this effort to actually build such a computer. And my colleagues at Microsoft are very involved in that. We have colleagues trying to build a chip to realize a computer, all the way up to quantum software to operate these new machines. You can download today a quantum development kit to plug into Visual Studio, for example. Recently, my colleague Anita presented a webinar on the subject, so I'll refer you to that the URL that you see on the screen here to learn more about quantum computer. What's interesting for us now is the impact of quantum computing on cryptography. Although quantum computing will bring a revolution in the information theory landscape, it will actually be very catastrophic for the world of information security. Indeed, a quantum computer, it's as if it was designed to break cryptography. One of the first quantum algorithms that was discovered by Peter Shor, and excuse my geekiness here by representing the great Peter Shor as Dart Shor here. He discovered in 1994 an algorithm to factor large integers and find a discrete logarithm of large integers, which are the underlying mathematical problems giving the security to the RSA and the DSA and Diffie-Hellman, the cryptographic systems. and also the elliptic curve variance of these problems. So using a quantum computer, one could break these very important security algorithms, and that would signify that most, or in this case, basically all of the cryptography we use on the internet today would be broken. That is your HTTPS, your TLS connections in your browser, your private messaging systems, your SSH protocol to connect to web servers, your bitcoins, your certificates, your software update channels. All of these would be compromised by a quantum computer. And estimates say that the quantum computer could be built within 10 to 15 years. So there are some people that think that a quantum computer will never be built. Some others think it might take, just 5 years. As security practitioners, we have to be prudent, and we have to take the worst case into consideration. And a decade-ish estimate gives us a good idea by when we need to migrate to something that is quantum safe. So we need to develop a new type of cryptography that resists a quantum computer. Not to say that is a special magical algorithm that no quantum computer could break, but just one that we don't know how to break with quantum algorithms. So you might wonder, why would we need to act now if we have 10 to 15 years? Why can't we wait 9 years and deal with it, just like we dealt with Y2K in the very last minute? If you're old enough to remember, we'll deal with that later, just in the nick of time to replace just before we plug in the new quantum computer. Well, the reason is that the data that circulates on the internet today is at risk, because let's say I'm exchanging data, communicating securely. An adversary could take this encrypted data, store it for however long it needs to decrypt it later with the help of a quantum computer. And we know adversaries around the world today are powerful enough that they're able to record large parts of the internet traffic. Secondly, updating standards in which this cryptography is used will take a long time. TLS, SSH, these are all developed by large committees, and everybody needs to agree, and we need to define new ways to use new algorithms and new mechanisms in these protocols. And another point is that to update the cryptography we use in our software, we need to test and realize the impact these will have. New cryptographic algorithms might have bigger keys, bigger messages, signatures. They might run slower than RSA, and also just physically modifying the algorithms in the code might be difficult. We had this experience in the past from migrating from, let's say, hash functions, like MD5 to SHA-1 to SHA-256. And sometimes it's just hard because there are assumptions made by crypto developers, hard coding all the algorithms in there, and we want to make it easy to move away from these. Now, taking all this into consideration, let's say you have data that need to be secure for a certain amount of time, let's say 10 years. You're communicating, you have health data with your hospital systems, your trade secrets, you have the secret recipe of Coke that you're communicating with your web servers. Then if this data needs to be secure for more than, let's say, 10 years, plus the time needed to change the protocols, plus the time needed to update the software, that's when you run the clock backward, and it gives you the start date at which you need to start migrating away from the current cryptography. And for many threat model, that means time to start is today, or even better, yesterday. So what are we doing about this? Well, it turns out that academia has been ready, has been expecting this, and I apologize for the small fonts here on this slide. I don't expect you to read any of this, just to give you an illustration of what's going on. NIST is the National Institute of Standards and Technologies. It is the standard bodies in the United States that dictates what the government agencies need to use as far as cryptography. But it is the de facto standard organization of the world because its standards get replicated all over the planet. And they made a call in 2017 for a replacement of our classical algorithms that are susceptible to the quantum computer. And they requested new encryption mechanisms, key exchange mechanism, and new signature algorithms. So a large body of researchers submitted proposals. There were 69 in the round one. It took some time, up to 2 years, to analyze these. Then they cut in a Thanos fashion here. Almost half of these, a bit more than half of these, and similar ones got merged together, and we arrived in a round two with 26 left in the race. And we are now just before the announcements of a third round, where fewer options will be, fewer algorithms will remain after a third round, and these will be further studied, and some draft standards will show up in 2022, so in 2 to 4 years. So we're really close to having a new set of proposals for replacements as far as quantum safe cryptography. So my colleagues at MSR have been very active in this case. You'll see in this slide I present 4 of proposals that we submitted to NIST in collaboration with other organizations and other researchers. So it's a big collaboration with academia and the industry. The first one is called ProtoChem. It is a key exchange mechanism based on the learning with errors problem. The second one is called Psych, which is super singular isogeny elliptic curves. This is the closest algorithm in all the competition it's the closest algorithm to elliptic curves, which is the current state of the art. So it has a very nice properties. In fact, my colleague Craig Costello has just recently presented a webinar on the subject, and I recommend you check it out if you want to learn more about this cryptographic system. We also have 2 signature algorithms. One's called Picnic. It's based on zero-knowledge proofs, hash functions, and block ciphers. I mentioned the Shor algorithm earlier that breaks all the asymmetric cryptography that we have. There is another type of ciphers in cryptography called symmetric ciphers that are, for example, block ciphers like AES and hash functions. And these ones are affected by the quantum computers, but they are not broken in a catastrophic manner, which can just double the key size or the hash size, and then we're able to resist the quantum computer for these. So Picnic, in this case, is based on these type of primitives. And lastly, we have a QTesla. It's based on the ring variation of the learning with errors, and it's a fairly efficient signature algorithms. So all of these, the goal of the webinar is not to go over all of these in details. They all have their own website with way more detail. So the goal of the webinar, however, is to say, okay, how can we use this new cryptography? How can we integrate it into our protocols and applications and services, and to protect the data that we have today against the quantum computer of tomorrow? Well, that seems a fairly difficult task given the number of algorithms floating around. How do you start? Where do you start? What do you do? So to answer this question, we joined this effort called the Open Quantum Safe Project. This is a collaborative open source project led by the University of Waterloo, and in which we developed a framework, a C library, that integrates all the new post-quantum algorithms. And in turn, we take this framework and we integrate it into popular application or popular open source libraries that develop or that implement popular protocols. For example, we integrate into OpenSSL and into Boring SSL if you want to try the new post-quantum algorithms into TLS. We also integrate into OpenSSH and OpenVPN. If you're not a C developer, you might want to try it from a different language. So we provide wrappers in C++, C#, Go, Java, and Python. And there are other ones in the work. So I invite you to go visit this website, openquantumsafe.org, for all the information and a link to our GitHub account. So given this project now, that allowed us to experiment with many of these algorithms, including our own, but also from different variants and flavors of algorithms in all these protocols, which are essentially the basis of every cryptography used on the internet. And I'm going to discuss next interesting results that we had into TLS and SSH. So the first question we asked ourselves is, what is the impact of taking these new algorithms and integrating them into these protocols? So elliptic curve, Diffie-Hellman, and RSA, we know very well how they behave and they perform into TLS and SSH. But these new algorithms, it's not so clear. Some of them have really large keys, some of them are really slow, some of them have big signatures, some of them use implementations that are non-common. So the first exercise was to try them all, essentially. But the trust we have today in the classical algorithms like RSA and DSA comes from the fact that they've been around for a very long time. Like RSA was developed in 1976, and the reason that everybody trusts it is because nobody was able to break it. It's a bit like code packages. We have trust in packages that have been around a long time, that have been audited by many different people, but the shiny new piece of software might not be the most secure because nobody looked at it. So it's the same for these algorithms. It might take a while to gain confidence. So the first thing we want to do when we're going to deploy these new algorithms is to deploy them in a hybrid fashion, a hybrid manner in which we combine the security of the classical schemes like RSA and DSA and Diffie-Hellman and combine it with a post-quantum scheme in a way that if either one is secure, then the hybrid combination will also be secure. And this is very useful because it provides us the security of the scheme that we have today, and it gives us a safety net in case we have to face quantum attack in the future. So how this is achieved is that in TLS, for example, if you share RSA key or ECDH, elliptic curve Diffie-Hellman key, you don't actually use the RSA key directly to encrypt the data during the session. What you do is you negotiate between the client and server at the beginning using that algorithm to derive a master secret that's used to derive an encryption key for AES, which is a very efficient symmetric algorithm. And then you can carry on the conversation using AES. So given that, we can do that conversation as we did before, but also in parallel have another one that negotiates a post-quantum secret. And then we can mix them in the key derivation function built in TLS, the KDF, and then out comes this hybrid key we can use. So it works well because TLS and SSH, they already have this ability to negotiate which algorithm you want to use. However, they don't have the ability to negotiate two algorithms at the same and be able to use them at the same time. So there are two ways we can go around that. The first one is we can define a new scheme like this on the screen, this new hello, my name is ECDHE P256 Psych P434. So what that means is that we can just invent a new scheme that instead of being ECDHE, the elliptic curve Diffie-Hellman, the ephemeral version, or Psych, and we can just say it's a new one that's ECDHE and Psych together. So what's nice about this approach is that you don't have to change the protocols, you don't have to change the implementation. You just define a new algorithm, and under the cover and the crypto library, you can do the ECDH operations and the elliptic curve operation, and the cyc operations, and then you can combine the results, concatenate them, and just present it to the TLS layer that sends it on the wire. And then when you get a message, you split them up and you operate ECDHE and cyc. And then that's completely transparent to all the TLS layer. So it's the easiest thing to implement, but also could result in a big combination of schemes, because for all the classical schemes you want to support and all the quantum ones, makes many combinations in between. Another approach would be to define a new mechanism to negotiate independently the classical and the post-quantum one. And that requires changes to the protocol and the implementation. So our paper goes over the various options, and I encourage you to take a look at it if you're interested in the details. But the important things to consider is when you do modify the protocol, you need to take into consideration backward compatibility. A lot of the TLS implementations are not only in software, they're also in the hardware optimization machines, and so you want to make sure that your modifications won't break these machines. Also, you have to consider the performance, the latency, the data flow. You don't want to add new messages for this negotiation or introduce new data flows that weren't there. So I'll spend a few minutes here to discuss the TLS case study. So TLS is arguably the most popular security algorithm. It's used everywhere. That's what protects HTTPS. And in our paper, and also that's what we've implemented in the Open Quantum Safe project, we have two integrations, one in TLS 1.2 and one in TLS 1.3. That's the one I'm going to discuss now. That's basically the new version of the protocol. In TLS 1.3, you only have access to the elliptic curve type of exchange. They've done away with RSA to preserve a perfect forward secrecy. So in order to use our post-quantum algorithms, we kind of have to cheat, and we masquerade as elliptic curves. So that's just a kind of a current workaround until the specification recognizes and allow other algorithms, which will be the case when NIST publishes these new standards. But for now, we kind of just pretend that we are elliptic curves. And then everything works very nicely. We integrate in the key share message that's highlighted in the little green square there, the key share extension. And we just expose our new algorithmic types, the new curves, and then that allow us to derive key for all the algorithms, for Frodo and Cyc and all the other ones. So TLS has built-in limits on how big things can be, how big public keys and signatures can be in the messages. So for example, it's 2 to the 16 minus 1 bytes for public keys and signatures, and certificates can be slightly larger, 2 to the 24. OpenSSL, for example, the implementation of the standard has smaller limits. It's mostly to prevent denial of service attacks, because RSA is the biggest one we had so far. Even though the spec might support bigger algorithms, in reality there's none. So the implementers decided to limit further down the sizes of the artifacts that are exchanged. So in our integrations, we've hit a few of these limits, and I'll talk about that later. But for the most of the post-quantum algorithms that we tried work nicely in TLS. And we have integrated that in both OpenSSL and Boring SSL, their test tools, client and servers, and also in Apache and Nginx. You'll see the link here on a GitHub project for the OpenSSL fork that integrates the Open Quantum Safe algorithms. And well, speaking of that project, I will just show you a quick demo now of a TLS 1.3 connection that has a hybrid key exchange. That's ECDHE using the NIST P256 curve, in a hybrid mode with a Frodo algorithm. And for authentication, we created a ECDSA P256 certificate as a hybrid with qTesla P1. Switch, now we should see the little console here. So cryptographic demos are quite often boring because not much is happening on the screen. It's not like a nice UI demo. So you'll see the connection and it'll just say it's going to work. But the main point of the demo is that if you've used OpenSSL, the main takeaway is that nothing changes. However you used to use the OpenSSL tool, you can just continue using it as is. You specify the new algorithms and all works. So the integration is pretty seamless. So that's the point of the demo. Here on the screen, you'll see that we have we'll start a server that's going to listen to offer TLS 1.3 connections. The certificate is going to use is a ECDSA 256 with qTesla, and that's it. So it's just going to launch that. Now it's waiting for connections. And in my other window here, I have the client ready to go. So the client is going to request a connection to that web server, and it's going to request a specific curve for the key exchange. In this case, ECDHE P256 in combination with Frodo. So when I start the client here, the request is going to be made, and there's going to be two negotiations in parallel, one ECDHE and one with Frodo, resulting in a successful exchange. Now I've run these tools in debug mode so we can see some output. So we in fact can see that TLS 1.3 was used. And if I scroll up a little to see the algorithms that were used, we notice that the signature that's protecting the exchange is indeed ECDSA with qTesla in combination, and the key that was used for the encryption was P256 and the Frodo hybrid. So voila, just like that, we're able to use OpenSSL with post-quantum tools. So the heavy burden of integrating the post-quantum cryptography was done by the OQS project, and you as a user, you can just go use OpenSSL as you did before, and you have post-quantum protection right away. So the second thing we looked at in the paper and the project was SSH. SSH is kind of more the same, so I won't spend too much time on it, but there's another key exchange, another authentication mechanisms in which we also provide hybrid mode, and there are also size limits. In this case, 2 to the 32 bytes for message sizes, which is bigger than in TLS. And we also have a GitHub project, a fork of the SSH project that gives you quantum safe cryptography. So I will also just show the tool. It uses the protocol SSH2 from OpenSSH 7.9, and instead of using Frodo and qTesla, now I'm going to use Cyc as a hybrid post-quantum algorithm in combination with Picnic. So it's interesting that Cyc is slightly slower than its other key exchange mechanism, and Picnic has slightly larger signatures. But for SSH, unlike TLS where you have many connections a second potentially, SSH is a very kind of a low bandwidth protocol. You communicate once with a server, and that's it. So it's slower algorithms are not penalized and might in fact provide better security in this case. So back to the console here, I have a very large command line ready to launch a SSH daemon here. That's the SSH server part, and I've pre-generated the keys here to simplify the demo, but I'm gonna only accept Cyc and ECDH and Cyc combination hybrid key exchanges, and the only signature algorithms I accept will be P256 ECDSA with Picnic L1FS. So the server is launched. It's going to ask me to authenticate. We don't want hackers to run my fake servers in my stead. So there it is. It's launched, and the client is also a very big command line ready to go with similar arguments. And again, the point of the demo is not to understand what's going on there, but understand that if you've used SSH, you can use it as you did before, and it's going to just work with the new quantum algorithms. Also running that in debug mode to see the output, and scrolling back up, we see that they've used the picnic key successfully, and here it is. The key exchange key I would use was indeed psych in combination with ECDHE, and the host signature key was indeed ECDSA P256 with picnic. There we are. So another interesting thing that we went through in the paper is to try all the algorithms that we had access to in the Open Quantum Safe project. And again, the goal here is not to read all of them. If you're interested in one particular algorithm, you can check the paper to see how it performed and how it was integrated, if there were some integration notes for it. But most of the key exchange algorithms work pretty well across the board in TLS and SSH. A green check mark means everything was fine. A yellow check mark meant that some messages were they're valid messages in the specification in the TLS and SSH protocol, but they were too big for the implementation. They reach a limit in OpenSSL in this case. So we just had to increase some buffers in the implementation, and it worked. Some others we couldn't make work. For example, NTS, which is a code-based system, and also the same thing for classic McLeese. It's simply too large of public keys, and they were hitting all sorts of limits inside the code base that we couldn't easily fix. For signatures, we had a lot more things we had to tweak, because the post-quantum proposed ones have larger signatures and keys. But most of them were able to fit after some modifications to the base programs, which is to be expected when you integrate new algorithms. And just very few couldn't work. So the one X red mark here in TLS was Picnic, the round 1 version. The Picnic team in the second round of the NIST competition made updates and provided new parameters that indeed did fit into TLS nicely, like Picnic 2 here. And the Rainbow algorithm had too big public keys, and they were providing some error failures here in SSH. So that was for just the integration of the algorithms themselves. Could we fit them? Another question that we ask ourselves is, what would be the performance impact of these algorithms? Would we hit, some algorithms are slower than others, so what would be the effect of these algorithms in these protocols? So we made we had another paper that discussed this. We created 2 experiments for TLS specifically. And one, we simulated some connections inside one big Linux machine, in which we control the latency and the packet loss rate. And the other one, we tested the retrieval of various size web pages across different VMs around the globe. So let me discuss this quickly. Another very dense slide. Apologize just for pretty graphics. You don't have to read the details. It's just to show kind of a trend, and the details are in the paper if you're interested. But what I'd like to just highlight for the first experiment is that without a full internet-wide system to test multiple clients with multiple servers, we decided to build this framework which allowed us to replicate these conditions in the lab. So with a Linux VM, with fairly large, with 64 cores, we used a characteristic of the Linux kernel, which is called the network emulator, in which you can control the network conditions. So you can add some latency, you can add some packet loss rate, and these type of things. So we created a virtual Ethernet devices for client and server, and using the OpenSSL S-Time tool to measure connection time to an Nginx server, we're able to measure the TLS establishment time for various round trip, the RTTs ranging from 6 to 196 for them, and changing the packet loss probability from 0 to 20% at various clicks. So what we observed is that for most cases, for fairly non-noisy channels, so packet loss rate smaller than 3%, everything was fine. It's faster algorithms perform well. But as we increase the error rate to 3 to 5%, then larger algorithms get penalized a little bit more because their messages need to be fragmented across multiple packets, and the chances that one of them will get lost and would require retransmission increases. So you see that in these graphs, the blue lines that takes longer are the ones with bigger keys in this case. So there's a lot of technical data in this paper. I encourage you to take a look at it if you want to see the details. The second experiment we had was to experiment with actual web page retrieval, because after looking at some surveys which said that typical web page is around 2 megabytes, so the cost of doing the crypto can be very small if you compare it with the total load time of a web page, especially if this web page is further away. So to test that, we add a virtual machine, a client that communicated with other 4 virtual machines across the globe, from one that was next to it, and one all around the planet in Australia. And we also measures to testing retrieving pages that are 1 kilobyte, 10 kilobyte, 100 kilobytes, and 1,000, which is 1 megabyte. And what we observed is that kind of as expected, the further away the connection is and the bigger the web page, the less significant the TLS establishment cost is. And why is that interesting is that I've been talking about using quantum cryptography, using it today in a hybrid mode to protect the data that's sent across wires every day today. And the question a deployer might have is that, okay, what's going to be the cost, not just of the development cost, but how slow the connection is going to be if I add a second algorithm on top of it. Well, the answer is that for most practical cases, if you're sending normal internet data, the answer might be not too bad. So all of these tests were done with hybrid key exchanges, combining the state-of-the-art elliptic curve ECDHE that's used today by itself, and compared with the same algorithm in conjunction in a hybrid mode with some other quantum algorithms. So that's kind of good news for experimenters that want to try these algorithms and see that the price to pay to get this extra protection is in reality not too bad. So these are basically things we can try today. So another fun project that we had was has to do with VPNs. VPN is an important protocol, and OpenVPN is a popular project that uses TLS for protection. So we integrated our OpenSSL fork into OpenVPN, and we're able to create this quantum secure VPN project. So what's that useful for is that there are a lot of applications, legacy applications, that we will not be able to modify because nobody's is working on them or developing them. They're just there. And so one way to protect their data is to wrap their classical RSA protection, let's say, with a quantum tunnel, with a quantum to tunnel the communication through a quantum safe VPN, and then voila, no quantum adversary will be able to break the encryption of the legacy application. In order to test that, we decided to make a little experiment. Some of our colleagues are working on Project Natick, which is a data center module that's literally quite underwater in the ocean on the coast of Scotland. And the goal is to bring the data closer to the customers and also, to use the cooling aspects of the ocean. And we ran an experiment using this OpenVPN project that's been running for a long time now, from our Redmond headquarters all the way to Scotland. And the reason we picked that use case is that that's a real life scenario of data center security, data center to data center security, and it's a test bed without real customer data, so we're able to experiment safely. And also, if we can make it work in this type of conditions, then we're confident we could make it work anywhere on the planet, because that little seal there that you see in the picture, well, that's the type of visitors we get to that data center, unlike cannot send a technician very easily down there. So you can read about this project and the Natick experiment at these URLs. And that's the OpenVPN integration. So, in conclusion, I think it's a fact to say that quantum computers are coming. As security practitioners, we have to be ready. We have to make sure that the threat model we have today will still be valid and will resist the quantum computers of tomorrow. So we have to make sure our cryptography is quantum safe. I provided a lot of information today on how we can do that, how we can move forward, not only at the academic cryptographic level, which type of algorithms should we use, but also how to integrate these new ideas, these new ciphers into our protocols, applications, and services. Give you a lot of links you can go and try and experiment with, and we're happy to hear back from you if you have comments, feedback, suggestions. You have my contact information here. The URL below is our team page with the links to all the projects you've seen in this webinar. So that concludes my presentation. I'll be happy to answer your questions in the live Q&A that follows. Thank you. Well, hello everybody. Christian Paquin. I hope you enjoyed this webinar. And we'll now be moving on to a live Q&A portion of the presentation. So I already got a bunch of questions that I've answered in the little Q&A widget in the webinar page. I'll be answering a few more for the next 15 minutes or so. First, I'd like to surface a couple of questions I've seen appear a couple of times. I'd like to clarify some of the difference between classical and quantum attacks, and also the difference between the post-quantum cryptography and what is known as quantum cryptography or quantum key distribution. So first, everything I presented today, post-quantum cryptography or quantum safe cryptography, are cryptographic algorithms that are just normal algorithms implemented with conventional computers, the same way you would implement RSA or ECDH. It's just that we call them post-quantum or quantum safe because we don't know, we're not aware of any way to break these new algorithms the same way that we know how to break RSA and ECDH with a quantum computer using the Shor algorithm. So the new label The only difference with these new algorithms is that we're not aware of any attacks. It doesn't mean they don't exist. In fact, we could break them with a conventional computers. They might have classical attacks that we don't know about. But until we find an attack, we label them quantum safe. And that doesn't mean because it was released, a year or two ago that we're satisfied. We'll need many years of cryptanalysis, both classical and quantum cryptanalysis, to gain confidence in these new algorithms. So that was the first question. The second question, a few questions were asking the difference between what is attack, like symmetric versus asymmetric crypto primitives. So symmetric primitives are like AES and SHA-256, the hash functions, the block ciphers. These ones are not susceptible to the Shor algorithm. There's another algorithm called the Grover algorithm that can be used to speed up exhaustive search on the key space. And in order to deal with that, you simply have to roughly double the key size or the hash size, and then you're safe. So we're not too troubled by these algorithms. On the flip side, everything that's asymmetric, not symmetric. So asymmetric crypto primitives such as RSA and everything that's based on discrete log, like Diffie-Hellman, elliptic curves. So these ones are completely broken. There's a polynomial algorithm against them. So these are the ones that we need to replace. I also got a couple of questions regarding quantum key distribution and why do we need post-quantum cryptography if we have quantum key distribution? Well, first, just to say what the QKD is, quantum key distribution, is a mechanism to exchange a classical key using quantum mechanics, and it's typically establishing a dedicated line between two parties, and then they can exchange a key securely and detect the presence of adversaries. The thing is that existed for a long time, and you don't need a quantum computer to run it or to break it. You can deploy that today. You can buy it. It's not compatible with the data models, the trust models that we use on the internet. We can't have dedicated lines between every client and servers that exist on the internet. So we use this PKI model that provides us trust that we can connect to parties that we don't know by verifying signatures that have been certified by a trusted party. So these signatures you cannot do with QKD, and the ones that we use today, ECDSA, for example, are not quantum safe and they need to be replaced. So QKD can still be in the run for taking over the industry. They have not succeeded so far, and the fact that we're migrating to post-quantum cryptography doesn't change anything about that. Okay, so these were some of the questions that were asked. Let me see. Yeah, there were some questions regarding the NIST round 3. So I've told you at the beginning of the presentation that NIST was doing this multi-phase standardization effort to find quantum safe algorithms, and nobody knows exactly when the next phase will start. And there's kind of a presumption that might happen really soon, maybe this summer. And we're not sure if we're going to go into a phase 3 or if they're going to decide on new algorithms right away. Presumably they'll have a phase 3, and there already been updates. Most of the quantum schemes that are still in the competition have made updates in April expecting a phase 3. And in OQS, in the Open Quantum Safe project, we've collected these, and we will start integrating them as soon as we're done with our current release, which we've just tagged this week as a release candidate number 2. So as soon as that's done, and we can put in the new material, and it will percolate down to all our depending forks like OpenSSL and OpenSSH. There was another question also we're asking, somebody was really worried about their Bitcoins, and I must apologize for putting that at the beginning of the slide. It's kind of a little bit of a, not teasing, but I'd like to make a distinction between encryption algorithms and signature algorithms. So encryption algorithms are kind of endangered today because everything that's encrypted with cryptography that can be broken by a quantum computer doesn't need to be decrypted today. It can be decrypted in 20 years when somebody builds an effective quantum computer. So your trust model, your data lifetime model might encompass, these decade period. So if you want the data to be secure in 20 years, you need to protect it accordingly today. But for signature, it's a bit different. You can't back authenticate or back sign something in systems with something 20 years ago. So in order to fool a PKI system to authenticate, to break a signature algorithm, you need an active attack with a quantum computer. So these will be more prevalent as we approach the day that a quantum computer can be built. And since in Bitcoin and these type of systems, a lot of the signatures are done with ECDSA, so these will need to be migrated over time, but not as urgently as we need to update the encryption keys in TLS and SSH because the data that's exchanged today is at risk using these. Let's see. Oh, I also had another question regarding how, if we in the Open Quantum Safe project, if we will implement or support other protocols than SSH and TLS. There were some questions about SMIME. So as you've seen, the Open Quantum Safe project is a highly collaborative effort. So a lot of the development is done on a volunteer basis. So anybody who's interested to contribute data is invited to do so. And I encourage everyone to go look at these resource links, either our Microsoft team, you just do a web search on MSR post-quantum crypto, and you'll find our page, or just go on the resource link to the right, and the openquantumsafeproject.org. And there you'll find all the projects we're working on. And if there is an application you'd like to test with post-quantum cryptography, well, either you can do the work and submit it back to our project, or you can ask us on our platforms on a GitHub to see if we can get somebody interested in doing it. So our general mandate is to try to anticipate what will be the changes, what will be the impact of migrating to post-quantum cryptography. And we're doing the incubation work now in order to avoid surprises later when it's going to be time to make the switch. And we're almost out of time, so I will answer one last question. This question I got at the beginning of the webinar related to hybrid modes. I discussed the hybrid technique in the webinar, in which we're going to we can combine a classical algorithm with a post-quantum one in order to get the best of both worlds. And we see that as really important as a first phase of transition, because even if NIST publishes new standards in in a year or two, then the industry as a whole might not be totally satisfied with the new algorithms, or will not trust it as it does the currently deployed one. So deploying in a hybrid mode we see is going to be of great importance to gain confidence during the transition, and while also protecting our data. So we'd like to see more work in the area, and we're certainly doing a lot of all of our prototypes use hybrid modes, and we'd like to get more feedback from the community on how's the best way to approach this problem. So I think I went over pretty much all the questions. So with this, I would like to thank you very much for attending this MSR webinar on quantum safe cryptography. As I said, I encourage you to visit the links that are posted to the right of the web page. And if you have any questions, feel free to reach out and engage either myself or the Open Quantum Safe project in order to take this work forward. And thank you very much.